Hi, so we are reading about zero phase transfer functions. And yesterday, in the last video, we discussed one way to implement zero phase transfer functions is with the help of um, uh, H hook Z, which means when you have poles and zeros on the as a mirror symmetry about the unit circle. Essentially, just to remind, what we had discussed is if my transfer function is of this form, right? Then the phase is 0 for all frequencies. Now let's study some properties of this H hook Z. Okay, H hook Z. So graphically, how do we say it? So we know we want the phase to be 0. This means H hook Z is, as you have seen, it's H1Z times H1Z inverse. So this is the same H1, right? The poles of this means wherever the Z is 0 in the denominator, there Z inverse is 0 in the denominator. I'll just give you an example. Consider this example, 1 upon 1 minus Z naught Z inverse. And then I will also have there is a pole at Z naught, then the equation will become 1 minus, let me keep it, HZ is this, right? So what does this mean? That my HZ inverse, well, what that will become? H of Z inverse will become equal to 1 upon 1 minus Z naught Z, right? So this one has a pole at Z naught, right? And where is this pole? This is a pole at Z naught inverse, right? Because when my Z is equal to 1 upon Z naught, then this whole thing is equal to 0, right? So this means a pole at Z naught induces a pole at Z naught inverse. So let us say I have a pole at Z naught somewhere here. This is my Z naught. Then the 1 upon Z naught, which will be somewhere here, 1 upon Z naught. I will have a pole here as well. Mirror symmetry. So this is called mirror symmetry about the about the unit circle. Okay, so let's look at one example. So now I know my H hook Z is, let us say, it's a rational polynomial, a rational transfer function. It means it has a numerator polynomial and a denominator polynomial, right? It has some numerator, let me call it as B1Z, and a denominator, let's say a B2Z, right? It's a rational transfer function. And now since H has a hook, I have put hook on both of these. Let us consider one such polynomial, let us say 1 minus AZ inverse into 1 minus AZ, right? Because this pole or this 0 will induce another 0 here. Okay, so what can we say about the form of this polynomial? So let me multiply this. 1 minus AZ inverse minus AZ plus A square, right? So what I see is consider this Z inverse and this Z, both have same coefficients, right? I can write this as 1 minus A Z inverse plus Z plus A square. So what I find is the coefficients of Z inverse and Z are same. Another way to look at this is that, let's say my H hook Z is equal to some H1Z times some H1Z inverse, means same H1Z inverse. If I now let's see H hook Z inverse, what will this be equal to? This will be equal to H1 of Z inverse times H1 of Z inverse inverse, which is same as HZ. So what I find, this is same as H hook Z. This is an important result. So this is the symmetry, that H of Z inverse or H hook of Z inverse is same as H hook of Z, right? So, okay, so two things we saw. One is this property and the other is this property. Okay, and I explicitly state it now. The coefficients of Z and Z inverse are same. And these kinds of polynomial are called symmetric polynomial. So these polynomials are symmetric polynomial. Symmetric means you make Z inverse or Z, they are same coefficients. Okay, so it is a symmetric polynomial. We denote it with a B hook, let's say, and B hook will be of this form. Z plus, so let us say it's a polynomial of degree capital N, then all the terms will be z to the power 1 plus z to the power minus 1 plus some coefficient z to the power 2 plus z to the power minus 2 of this form, right? Or it could be also, so both these representations are valid. In this representation you have z plus z inverse to the power L, where L goes from 0 to capital N, right? And the other thing is that interchanging z and z inverse does not make any change, right? This is symmetric polynomial. Okay. Now, how do you implement? Now coming to the question, this H hook Z, how do you implement it with, let's say, an LCCDE, right? This is the way we, using LCCDE, we implement our transfer functions, right? How do you implement it? So a causal implementation is not possible. Why? So let us recall what is the meaning of causality. Causal means it is implementable in real time, right? And it means my ROC is basically outside the outermost pole. So you remember in Z transform we talk of ROCs. So let's say this is a pole. So by mirror symmetry we'll have a pole here. So my ROC will be this region. Means this region is my ROC for causality. Right? But then there's another condition called stability of the system, right? If system is not stable, you will get, it will explode, the output will explode. So for stability of the system, you need your unit circle should be inside the ROC. So if there is another region, so this is the region for stability. Let me use red pen. So for stability, the ROC should be here, but for causality, the ROC should be here. So means you will never have an ROC or a region where both properties are satisfied. Generally, in filters, we need stability, right? So stable implementation is not possible, means we cannot have a filter. Okay, so to make it stable, we have to give away the causality property. But if we give away the causality property, which means we cannot have an online application, a real-time application, right? Because just to remind you, the causality means yn is a function of, right, xn comma xn minus 1 comma so on up to xn minus capital N, some capital N, right, comma yn minus 1 comma yn minus 2 and so on, right? It cannot depend on future values, right? That is the meaning of causality. Okay, so I hope this is clear. So let us see some examples so that you are more clear. That causal implementation is not possible. Let us say my HZ is 1 upon 1 minus AZ inverse, right? Just one pole at A, right? This is a pole at A. Okay, and my H hook Z, the symmetric version of it, the zero phase transfer function of this will be 1 upon AZ inverse times 1 upon 1 minus AZ inverse times 1 upon 1 minus AZ, right? So this has a pole at A, this has a pole at A inverse, or 1 upon A. Okay, now can we have a causal implementation? How do you find causal implementation? You will say YZ upon XZ is equal to basically this form, which is 1 minus a times z plus z inverse plus a square, right? Now, when z will go there, it will become yn plus 1. And I don't want yn plus 1 there. Let me try to make it, let me multiply everything with z inverse. So this becomes z inverse. This becomes z inverse. This becomes e to the power minus 2. This becomes 1. And this becomes z inverse, right? So now it becomes my my yz becomes, so if I take an inverse z transform, it becomes y of n minus 1, right? Minus a times y of n plus, inside the brackets, y of n minus 2 plus a square y of n minus 1 is equal to x of n minus 1. Yes. So now, if I try to implement it from yn, this implementation will be causal, but this implementation won't be stable. On the other hand, if I don't do this z inverse multiplication, I simply do y of using the same form, which was yn plus, minus a times y of n plus 1 plus y of n minus 1 plus a square times yn is equal to xn. If I try to implement it in terms of yn, this will be a stable implementation, but it won't be causal because it needs yn plus 1, which I don't have. Okay. So basically, to give you, this was an example to give you an idea that we cannot have an implementation which is both stable as well as causal. Okay. Let's see. Yeah, so we cannot have a causal implementation of this. So to have a stable filter, I have to give away the causality property. Okay. Similarly, I can try with this example also. You will get similar results, that you cannot have a causal implementation for this stable filter. If it is a stable filter, we cannot have a causal implementation. Okay, so the solution for this is time reversal filtering. That will be the topic of our next video, that how do we implement zero phase filters in an offline fashion. Means we give away the causality property. We cannot have a real-time filter. Means we cannot have a real-time where yn depends only on the past values. So yn has to depend on future values. Then we use this. We can do this process in the offline mode, and we will see the next video. Thank you.